AC Corrosion, Integrity Aspects and Cost-Effective Mitigation Measures by Lars Vendelbo Nielsen and Andreas Junker Olsen. The people behind the presentation are Andreas Junker Olsen and Lars Vendelbo Nielsen. I, Andreas, am a corrosion engineer at MetriCorr. I have a PhD in AC corrosion of cathodically protected pipelines and have written several peer-reviewed papers on AC corrosion. Lars is the CEO of MetriCorr, has done more than 20 years of AC corrosion research, and has chaired standardization committees with NACE, CN, and ISO on AC and DC interference issues. Presentation outline. We'll start with an introduction to cathodic protection, and then we'll have a look at what are the effects of AC interference on cathodic protection, and how does the combined effect of cathodic protection and AC interference lead to AC corrosion. This will be illustrated using a case study. We will then look a little at industry standards. What are the criteria listed in these standards in order to mitigate AC corrosion, and what are our options in order to be compliant with these standards. Finally, we will present the MetriCorr solution to cost-effective AC mitigation. This includes corrosion rate measurement, remote monitoring, and last but not least, knowledge. The presentation will be finalized with the conclusions. Over the next few slides, I will explain the basic principles behind cathodic protection. This is important because AC corrosion is strongly influenced by CP. Here we have corrosion. An anodic reaction takes place, iron is dissolved from the surface, and current runs in the direction of the red arrow. If we invert the direction of current flow, a cathodic reaction takes place on the surface. In this case, it's hydrogen evolution and production of OH- that makes the steel surface and the surrounding environment alkaline. For pipeline buried in soil, CP is realized by introducing an anode and a rectifier, as shown in this simple diagram. Current runs from the anode towards the pipe through the soil, and electrons run through the wired connection back to the pipeline. If we introduce a pipeline coating, the amount of steel surface to be protected is dramatically reduced, and so is the protection current. CP will protect the coating defects. Coating defects will become polarized in the negatively polarized and alkaline. Cathodic protection can also be illustrated using the Poe-Bay diagram. If we consider a point in the middle of the diagram at the open circuit potential of steel and the neutral pH of 7, this is in the corrosion domain of steel. When cathodic protection is applied, the potential is lowered, and once the hydrogen evolution line is reached, hydrogen evolution will cause an increase in the pH, and the pipeline steel potential and pH will follow this line into the passivity domain. The transition from corrosion to passivity corresponds exactly to the standard CP criteria of 850 millivolts. It's quite simple actually. The application of cathodic protection and high-quality pipeline coatings is an extremely effective tool to mitigate corrosion of buried pipelines, and it has been effective for many years. But what happens during AC interference? AC interference strongly affects the cathodic activity of CP pipelines. This process is known as Faradaic rectification. Faradaic rectification can be illustrated by comparing two different probes in a transparent simulated soil solution. The two probes experience the same levels of cathodic protection, going from negative 950 millivolts to negative 1250 millivolts, with or without AC interference. A pH indicator has been added to this solution to show when it exceeds a pH of 9. Now, following the timeline at the bottom, we can see that at 950 there's a small pink coloration on both surfaces. When we go to 1050, it gets more pink on the left-hand side. On the right-hand side, with the AC interference, there's enough hydrogen evolution to generate a pump effect that drives the alkaline environment upwards in the solution. But it's clear that the cathodic activity is enhanced by the presence of AC. Going to 1150 millivolts, the area increases on the left. On the right, the area increases a lot. Going to 1250 in a minute, we'll see that the area on the left-hand side, without AC interference, has caused alkalization of the environment around the probe surface. On the right-hand side, we have seen that the cathodic activity has colored a large volume in the experiment pink. This proves that the cathodic reaction at CP is strongly enhanced by the presence of AC. Process has many names, one of them being the autocatalytic nature of AC corrosion. The process is best illustrated by looking at such a wheel like this, powered by 3 external engines. The rotational speed of this wheel can be interpreted as an analogy for the AC corrosion rate. This is also why AC corrosion is evaluated in the industry standards based on the AC and DC current densities. Very often, in an AC-DC current density plot like this. Now, different standards outline different regions in this plot where the risk for AC corrosion is high. If we consider a small point at the lower part of the plot, then we see that once we experience increasing levels of AC interference, we're not only increasing the AC current density, we're also increasing the DC current density. And we very often find ourselves going towards this area of high AC corrosion risk. So how do we know this? So what to do about this? We have developed at MetriCorr a system comprising an interference corrosion logger connected to 1 to 2 electrical resistance ER probes. And this system, which fits inside a standard test post, continuously measures the corrosion rate by ER technology, the on potential, the off potential, and the IR3 potential, the DC current density, and the interference AC voltage, the resulting AC current density, and the spread resistance. In other words, effectively all the parameters of the wheel on the left-hand side. The ER probe is designed as the worst-case scenario coding defect with respect to AC corrosion with a size of 1 square centimeter. The system has a battery life of 3 years or solar power option for monitoring in the field. Now, let's take a case study. This one has been published before in the World Pipeline magazine in 2018. It illustrates how installation of 5 remote monitoring stations with ER probes along a pipeline heavily interfered with high voltage power lines by parallel high voltage power lines. Looking at this, we can on the left hand side see the AC voltage, the DC on potential, and the spread resistance, essentially the 3 engines of the AC corrosion wheel analogy. On the right hand side, we see the current density, the resulting current AC and DC current densities and the current density plot, and the size and color of the data points for each of the 5 sites illustrates the corrosion rate. Now, on this pipeline, we were given 2 options. The pipeline already had AC mitigation installed. We were able to switch this system on or off, and we were also allowed to play the cathodic protection level from high being negative 1.6 volts and low being 1.2 volts, around 1.2 volts. And as we go, we can see that at high CP, we sit around here, but once we reduce the level of CP, all the data points move towards the left. We see very little if any at all, corrosion from the ER probes. Now we're going to turn off this AC mitigation and increase the level of CP, and all the points immediately shifts towards higher AC and DC current densities, and one probe ends up in the high corrosion area. When we reduce the level of CP again, the point shifts towards the left in the diagram for lower current densities, and eventually the soil system stabilizes. That is, the pH decreases enough for the points to exit the high risk area. If we increase the CP again, we're immediately back with high corrosion rates. Turning down, we're going the opposite way again. We reconnect the AC mitigation, and corrosion is completely stopped at the end of the experiment period. Now, this illustrates the effect of adjusting these 2 engines of the AC corrosion wheel, the CP level and the AC interference level. If you find yourself in a case with an interfered pipeline, how are you going to mitigate AC corrosion? Grounding installations or CP moderation? Consider a pipeline with an interference voltage profile like this, assuming the same soil resistivity all over, assuming the same spread resistance all along. You're going to see an AC current density profile like this. Installation of grounding at the sites of the most AC interference will reduce the AC interference level and also the AC current density. This takes a lot of analysis and computation power. It takes a lot of time, and it takes a lot of digging to do that installation. At the end of the day, it's going to cost you a lot of money. The alternative to doing that is CP moderation. Simply by turning the CP knob on your turning down your rectifier, reduce the AC current density level along the pipe due to the increase in spread resistance without changing the AC interference profile. You can then install test posts with monitoring on specific sites of interest where the AC interference level is high or the natural soil resistivity is low. Is it really that easy? Let's have a look at the standards. The ISO 18086 and the NACE SP12424-2018 are some of the most the governing standards on the topic. At a first glance, these look quite different, but if we take out the criteria from these standards, as they're listed below, we see that both standards state that compliance with general CP criteria is mandatory. Reducing the interference voltage may be necessary by AC mitigation. Both standards agree that corrosion is essentially governed by AC and DC current density limits. But this is where it gets interesting. Both standards also say that effective control of AC corrosion can be shown by documented small corrosion rate by whatever means available. This essentially means that if you can document that you have no corrosion, you can disregard the current density criteria. Disregard. Going back to this figure, our options to mitigate AC corrosion on pipeline are these. We can reduce AC interference. We can twist this engine, modify this engine. This can be reduced up to 5 times. This is the most common method, but the cost is extremely high and the effect is limited. Another option is to optimize pipeline bedding. This can only be done during destruction, and very often the soil is what it is. High resistivity soil that would limit AC corrosion may, on the other hand, hinder the optimal CP operation. Now finally, CP operation can be optimized to prevent excessive CP and prevent an increase and cause an increase in the spread resistance by up to 25 times. That's 5 times, potentially 5 times more effective than AC grounding installations. Continuous monitoring with corrosion rate measurements can be implemented for verification of both CP effectiveness and standard compliance. And this is the MetriCorr, this is our proposal for cost-effective AC mitigation. The system comprises data loggers and ER probes. The data logger is dimensioned to fit inside standard CP test posts and blah 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 blah. Data is transferred to an online environment where you can access data or have data transferred directly to a SCADA system. The online system offers customizable alerts for all log parameters, most importantly probably being the corrosion rate. The online tool also offers visualization of data in graphs for effective analysis, interpretation, and verification. The shown example here is a field case. Again, a field study, a field case of overprotection and AC interference. The AC interference is around the pipeline was interfered with up to 5 volts AC. The on potential is very negative, about 1.75 volts. As a result, the cathodic current density was extremely high, up to and increasing up to 70 amps per square meter. Therefore, the spread resistance was lowering dramatically, causing the AC current density to increase despite relatively constant AC level. The ER probes immediately identified high corrosion in the periods of high AC interference. This is a classic case of AC corrosion. We then advised the operator to reduce CP to 1.1 volt, negative 1.1 volt. As a result, the cathodic current dropped instantly and eventually reduced to below 1 amp per square meter. As a consequence, the spread resistance increased dramatically, and therefore the AC current density decreased back to below 100 amps per square meter. Corrosion was shown was stopped after just a few days at this reduced moderate CP setting, and all of this is in spite of a constant AC interference level around 5 volts. In effect, AC corrosion mitigation is achieved, and this is without installation of any grounding devices. Conclusions: the driving force behind AC corrosion is AC interference. AC current enhances the cathodic reaction. The cathode reaction lowers the spread resistance and AC current is increased. This process repeats itself, and the high current AC and DC current densities is the driving force for it. Is what causes AC corrosion. The intuitive thing to do when experiencing AC interference is to lower the level of AC interference. Is try to bring down that level of AC. This comes at a high cost. The second intuitive thing to do is to increase cathodic protection. Because a threat to pipeline integrity should require more protection, right? Wrong. This is not advised since this may accelerate AC corrosion. Instead, the scientifically proven and sound thing to do is to moderate cathodic protection, and consequently, this will lower the AC current density at the pipeline. This comes at no cost. Comes at no cost to the pipeline owner. Now, remote monitoring units with corrosion rate measurements can be used to verify the mitigation measures and effective CP operation in perfect compliance with available standards in the field. All it takes is a little bit of AC corrosion basics and the necessary tools to implement that knowledge. Thank you very much for having listened to this presentation. I hope it's explained a little. If it spiked your interest in knowing more about remote monitoring and corrosion rate measurements for AC corrosion control, please visit www.MetriCorr.com for more information. Again, thank you very much for listening today.